Just a reminder of the outline for lecture. This one we addressed for lunch, where I showed you the relation between current, voltage, efficiency, and quantum efficiency. So now we will mainly speak about open circuit voltage and zoom a bit more deeper into the solar cell, go to a much smaller scale, and talk a bit more about these charge transfer states. So, I just briefly, I mean, in the previous talk, I just said there is new absorption and new emission coming in the band gap if you blend a donor and an acceptor. So now, is this really true? Is this always true? If you blend a donor and an acceptor, will this always happen? Well, we don't know. But these are the material systems where I was involved in, which we tested if we can see new bands appearing in the band gap. For example, a Pantacene C60 bilayer, so they're evaporated on top of each other, Pantacene and C60. We made a device, measured the external quantum efficiency, and measured it really deep down into the gap. And you see this extra shoulder coming here. So for Pantacene C60, also there's a new state. Well, note that this thing absorbs 10,000 times less than the main absorption. So it's not going to contribute to current, but it's there. It is going to emit. A non-fullerene system, for example, again, a bilayer. This is H2PC and PTCBI. This is how the molecules look. They look, well, different from these, I think. And also there, you see a new band sticking out. Well, let's go back to bulk heterojunctions. You blend PTHT with this molecule. Again, here, you see the PTHT absorption. It doesn't go straight down. Again, there's a shoulder coming out here. So this is not PCBM. And two polymers. This is a polymer-polymer blend. Again, this is MDMO-PPP. Normally goes straight down. Again, you see new stuff appearing. And if you look at the emission for this one, I also plot the emission. You see, this is the emission of the acceptor polymer. This is the donor polymer, and this is the emission of the blend, the red curve. So I just want to show you this. We cannot test all donor-acceptor combinations, but these are the ones, or an overview of the ones we have tested, non-fullerene, fullerene, different donors. It seems that always there is something there in the band gap. It's difficult to detect. You need a special technique for it. I mean, you have to measure your EQE very sensitive, and you need to be able to do that. It has a really low absorption coefficient. And for the emission, it's also difficult to detect because it has low quantum efficiency of emission. And as I said before, it's not good to have stuff in the band gap for VOC at least. Just why do I call this a CT state? Well, you had time now to read it. I am going to read it also. What is a CT state? Why do we call it a CT state? Because what we see is an electronic transition in which a large fraction of an electronic charge is transferred from one molecular entity, which is the donor, for example, if you look at CT absorption, to another molecular entity, which is the electron acceptor. And in some cases, the CT absorption band is masked by the pure core. Well, the cases I've shown you, you always saw an extra band. Well, you can say, are you sure this is a CT absorption band? Because you can have maybe all kinds of stuff absorbing in the band. Yeah, why is it exactly this one? Well, you can check if it is a CT transition, for example, CT absorption. That's a transition like this. The spectral position or the energy of the CT absorption or emission, it should correlate with if you increase the lumen, for example, or you move the HOMO down, you should be able to shift this absorption more into the gap or out of the gap. Same for the emission. So I'll give you two examples where we vary the energy levels. Here is we vary the energy level of the donor. This purple one is PTHT. Here's the main absorption of PTHT. This small bump is the fullerene absorbing. And then you see this broad feature, which we attribute to CT absorption. Why do we attribute this? if you use another donor with the same optical gap, see here's the same optical gap, but the energy levels are different, this extra one blue shifts. That's also what you expect, because we lower the HOMO, it's jump higher in energy. So this is when we vary the donor. You can do the same thing on the other side. If you vary the energy levels of the acceptor, you can buy this PCBM now. You know all about that in case one was talking. Then you move up to LUMO, and then you see this extra band moves to the blue. So it's these reasons, and the fact that we observe them almost in all donor acceptor combination, is why we attribute it to a CT transition, because it depends purely on the interface. Because if you change the interface, that's how you can tune it direction or emissions.
On the one on the right, for instance, how do you distinguish between a change in intensity versus a change in peak position?
That's a good question. That's a question we have too. Actually, that's where we come next to. And here's the question. It's basically related to the question you asked. Where should we take the band gap of this donor acceptor black? Wait, let me push it over. Yeah, should we take what is now the band gap or the gap of this blend? Is it the optical gap of the main absorber? Should we take it at the peak of the CT absorption? Should we take it at the peak of the CT emission? Or somewhere in between? This is not an easy question. I actually can't know. I mean, it took us very long to try to figure something out. But it's just very, it's a whole good story. There are 24 answers. Well, I should have asked you guys before we did it. It took us like 2 years to figure out where it is. Most people say this one. But I have 16 people say this one, and then it's been equal. People are still voting, it's still going up. Some people say this, and it's basically equal. 5 people say this, 5 people say this, 5 people say this one. Well, what I would say is the correct answer. You could say the optical gap of the main absorber. That's the band gap for the current, because this little thing doesn't. It's negligible the light it absorbs. So for the current, I agree with you. Take that one. I actually added this answer yesterday evening. I thought, yeah, this is true actually too. But to get the optical gap for open circuit voltage, we choose this one, and I will show you why in the next slides. Therefore, I want to show you this slide. Now you have to really think on the molecular scale. What is happening when we excite into this extra band, this very low absorption? You start from a material in its ground state, which just means it's in the dark. And you have a very small chance, that's why it's a weak absorption, that you can excite this to the charge transfer state. The charge transfer state is the hole of the donor and the electron of the polymer, on the fluorine, for example, like this. So immediately upon absorption, you create this. But this is not stable and will relax. I mean, the bonds taking the electron, the bonds of the fluorine taking the electron, they will change, they will get a bit longer. The environment might adapt to this charge, which all of a sudden appears in the material. This is what's called reorganization, with a certain reorganization. This is what's called the CD state, or at least a relaxed CD state. So that's absorption. If this thing will emit, it's gonna, this thing, this one, the electron's gonna fall into the hole, and it's gonna disappear, and what's left is this rearranged environment around it. That's a bit higher in energy than the ground state, otherwise this would be ground state. So this one relaxes to that. So this is why absorption and emission usually in organic materials are shifted. The emission is always at longer wavelengths than the absorption. So the absorption is at longer. The absorption is at higher energy than the emission. So which is the energy of the CT state then? I would say it's this. The difference between the ground state and the relaxed CT state. So how do you get that from absorption and emission spectra? Well, yeah, if you want to have this was really in image, in pictures. If you want to have it a bit more abstract, usually they draw these potential wells. And the ground state is at the bottom. I mean, you're in the bottom of the potential well there. That's where most states are populated, of course, most of the population. The CT state, true, and the parabola are shifted. This is basically where they come from. You might have seen these things. So the energy of the CT state is the difference between the bottom and the parabola. Yes.
Excuse me, what is generalized coordinate?
Well, that's to make it ourselves simple. For example, generalized, this coordinate could be the bond length. So the equilibrium bond length for a CT state when you have charges is a bit longer, for example. But it could be all kinds of other stuff. I mean, the environment also adapts. This plot normally should be a 2D plot, it should be multi-dimensional. But I mean, you have potential wells. That's what it's schematically depicts. So you can now, if you read papers about this, how should the absorption spectrum look and the emission spectrum look for something like that? Well, the theory predicts that it's Gaussian absorption bands for this. And the peak of the absorption will be exactly this length here. So you see, the peak of the absorption is the energy of the CTC plus this reorganization energy. The peak of the emission is the energy of the CT state minus this reorganization energy. So where is the energy of the CT state then? Well, it's in between. It is where absorption and emission cross. That's where it is theoretically. So how can you get the energy of the CT state then if you do measurements? You can do it like this, like I plot here. You plot the absorption and the emission, you see where they intersect. If you only have the absorption spectrum, you can still use this Gaussian and fit it to the curve. And this is how you fit it to this to that lower energy part. And this is also a way to get the energy of the CT state. That's usually how we determine it. How well does this work, or what do you, well, if you do this, so we did it for three material systems, and here in this last material system, we just varied the stoichiometry. If you add a bit less PCBM, your voltage is slightly higher, the energy of the CT state is slightly higher. So we vary, here the temperature is varied. We take these high sensitive EQE spectra, we look at this little Gaussian, we fit our Gaussian formula to it, and we determine like this the energy of the CT state. It's a bit temperature dependent. It might be due to disorder. We don't know why. I mean, also the optical gap of silicon is temperature dependent. This is not really normal. But now we have an expression, an analytical expression for this low energy absorption band. So remember from previous lecture, you can fill it in because this, again, it's the low energy part of the EQE spectrum. You can fill it in this expression for J0, which we had before, J1, which was mainly determined by the low energy part. You have to multiply this by the fast increasing exponential. So you get an analytical expression for the open circuit voltage. You can fill it in. It's a big beast. I will try to go gradually into it and show everything. But the first thing you notice is that there's a temperature dependent part. There's a light intensity dependent part, or part dependent on how much current at short circuit comes out. And so the temperature dependent. So let's look at the temperature dependent part. If we lower the temperature, VOC should rise. Yeah, that's what happens. So this is VOC measured at different light intensities. And you see that VOC indeed rises if you lower the temperature. What should also happen is if the temperature is 0, VOC should be, they should merge together. And this is what you see. They go together. So this makes us slightly confident in our definition of ECT. We prefer this definition over the peak of emission or the peak of absorption. We want to put one number on this whole band, and this is how we do it. Because of this reason, because this works. So now let's go deeper into this expression which we got for VOC. So it contains this part, the temperature dependent part and the temperature independent part. This is the energy of the CT state as defined as previous. This part contains here this parameter F, which I didn't say anything about yet. F just means how strong is it absorbing, how intense is the CT band. So if you play with F, you should be able to play with VOC. You have to play a lot with F, so the intensity of the CT band, because it's in a log. It's in an LM. So if you change this by a factor of 10, and kg times LM 10, you can only change it by a factor of 60 millimoles. So you have to play with this one a lot. And then there's the non-radiated parts. Well, the CT state is not the only part of recombination. There are lots of non-radiated recombination. This will lower VOC too, as I said before. So this schematically said, what do you want for a high voltage? What do you want? You want the energy of the CT state as blue as possible, as high as possible. Well, it's linear, right? We'll see some examples of that later. The energy of the CT state is approximately related to almost donor minus the donor-acceptor, as we see before. What we also want is, if you can't move that, let's try to push it down. For example, of that too. And that will also influence the open circuit voltage, although to a much less extent because you have this LM. How can you do that? What determines how high the CT absorption, how strong the CT absorption is? Well, if you have a lot of interface, you will have a lot of interface absorption. So lower the amount of interface is good for VOC. I don't say it's good for the current. What you can also do is put the polymer further away from the fullerene somehow, at least in your head you can do it. Then the wave function overlap will be difficult. It will be more difficult to push the electron from the polar to the fullerene or the other way around, from the fullerene to the polar. So pulling them further apart is good for VOC. What it does to the current, I mean, I'm only talking about VOC here. So now there will be three cases. Now I will present three cases. We will see what aggregation of P3HT and P3HT PCBM solar cells does to VOC, and which are the parameters which are changing. The second one is if you add more fullerene, usually what lots of people absorb in lots of systems, the more fullerene you add, the lower the voltage. We'll see why that is. And then the last one is about is about evaporated, co-evaporated. So first, P3HT. This is what you observe if you make P3HT PCBM solar cells with the same ratio. But you use radiorandom P3HT, you use non-annealed regular P3HT PCBM from chlorobenzene, for example, where the phases, the layer has quickly dried, so you still have some more space in it, or you still have less crystallized in there, or a very well annealed P3HT PCBM. Current goes up, maybe that's obvious. But if you use a calcium, aluminum electrodes, or right electrode, the voltage drops. So this is a quick question. Which property do you think has changed? What do you think? Do you think that the energy of the CT state has changed if it crystallizes more? Do you think that will vary energy levels? Or you will think it will vary this F parameter, the strength of the CT band? And I mean, which one is the most, maybe both properties have changed, but which one is the most determining one for the open circuit? Right, it's basically 50-50. No, it isn't. I mean, it's also, you can't know. It's important for me to see what people would think which has changed. So this is basically what we see if you do this high sensitive measurement on these solar cells. The thing redshifts. This extra band, it becomes more and more pronounced. If you do the fit and you plot the energy of the CT state, that one drops. So apparently something is changing at the interface which stabilizes or which makes the energy of the CT state lower if you crystallize. And it correlates with the voltage. I'll show you another more correlation. So the answer was that was A. And it was not E, someone said E. Normally, we can do more aggregation study. Aggregation study is in fact, I don't know if you know, if you have P3HT or the shorter side change forms, and you can add non-solvent to a solution, and you can pre-aggregate them in solution. For example, right here you get these fibers and you sprinkle the dilute solution with that. So this is what you get. If you heat up your solution and you sprinkle the hot solution, you have amorphous regions, more amorphous regions at least. So you break up some of the fibers, you keep some of them. So by varying the temperature of the solution, we can vary the fraction of fibrils. And we can actually quantify that. So here's the fiber fraction determined by optical methods from the solution. If you have very low fiber fraction, you see, this is the blue one here. If you have a high fiber content, it really sticks out. So the energy of the CT state changes. We did this for these three materials, and if you want to compare now these three materials, you have to compare them at the same fiber fraction, of course, because that's actually more varying than the difference between the three materials. So at a fiber fraction of half, which we approximately have for all of them, see that also between those three materials there's a slight difference. If you plot all that, the energy of the CT state is plotted here in the black, and the VOC is plotted in the open squares. If you do that, you see it's mainly correlated to the energy of the CT state. That difference P3H2 is also pretty easy. Right, so that was for crystallinity. Now composition. I don't know if people notice people working in the OPB. If you add more polymers, again the old one, if you add more PCBM, VOC goes down. What we see if we do this measurement and we look at this extra band, we also see that the CT band redshifts again. So again, the energy of the CT state drops and the VOC goes more or less along. How do we know it's crystallization in this case? Or is it even? Could be something else. Well, we did the same, this is, yeah. It has been observed, the same thing has been observed for other polymers, not only MDMO, PPB. Also, they see VOC drop if you add more PCBM, and they can also measure the energy of the CT state. In this paper, they do it from the peak of luminescence, which is not going to be exactly the right definition of energy of the CT state. Anyway, they see a similar correlation. Well, we did the same experiment with this fullerene. It's not PCBM, it has something with really long, it's C12 here, so it has long side chains. This, if you sprinkle pure films with this molecule, it does not like to crystallize as much as PCBM does. We're not even sure it really does form fullerene aggregates. What happens is here, the energy of the CT state does not change, or not change much, if you add more of this one. And you see VOC stays high too. thing is, this doesn't crystallize, so unfortunately we couldn't keep the high current that you had for PCBM. So overall, this fullerene acceptor is worse for the whole solar cell. It's better for VUC. So again, here's again crystallization or aggregation of the fullerene lowers the energy of the CD state. And for the feature HT, I hope I'm showing crystallization of the donor lowers the energy of the CD state. Actually, we in the 3 labs I've been, we took basically all polymers we could find, landed with PCBM, landed with PC70BM, anneal, landed the energy of the CD state in the way I described, and measured VOC at one sun, of course, because VOC is temperature light. And this is what we get. The electrodes are always IGOP to PSL or lithium fluoride aluminum good electrodes. Or what we think is good electrodes. And you see they're on the line, even though, I mean, they shouldn't be on the line. It's just VOC correlates most with the energy of the CD state, and we're not playing much with these two. The variation of these two is very small. Approximately, so we calculated, approximately, this is always 0.25 volts, and this is always 0.35 volts, or a bit more. Yeah, you can quantify that. So that's bad news, I guess, because there's always a difference between the energy of the CD state and VOC of 0.6 volts or electron volts, which is that's a lot. That's a lot we lose, and a big part of it is no way to frequently. And the other part is this, and we're not really playing with it. This one is what I call the radiated part, because it's not the non-radiated. So now the last of the cases. There was a recent paper coming out of almost pure C60 solar cells, or C70 solar cells. So what they did is they evaporated C60 with a very low amount of donor. You say that would never work. Well, apparently it works even better if you lower the amount of donor content. The main absorber is C60. C60 has a it's yellowish. So from 500 millimeter gold starts absorbing pretty strongly. If you do it with C70, well, C70 is even better. Is a better absorber than C60. They're both not really good absorbers. But anyway, I think they were able to make pretty high efficiency solar cell with something which is almost purely C60. Use a low amount of absorber. So this is up to me. I mean, it's amazing that it still works. This is how I mean, in 2D for me, and this is how I picture it in my head. You have a very low amount of blue balls to donor, and a huge amount of red balls to accept. They might be, they're probably isolated, blue balls. And if you go to 5%, it's like this, and if you go to 1%, there's 1 in this area. I mean, the solar cells that work, actually the 5% one was the best. This is, I mean, more in Dresden, they actually confirmed this. They make these devices, and it's really true, the low one works the best. I'm not going to address why the low one gives the highest current. I was mainly interested in the voltage here. You see, for the lower concentrations, you get a higher voltage. So, what do you think? Which one has changed? Most people think it's B which has to change. Well, let's see. So we did the measurement. This is all C60 absorption. You don't even see the donor. And here, this is what happens from 10% going to 1%. So 10%, and almost it just halves, 10 divided by 5. So, I mean, this is changing the intensity of the CT line. We're pushing it down by having less interface. Well, maybe you see here there are the fits. It's not very clear from the absorption where the energy of the CT state is. It looks like the peak is at least at the same position. This is the emission. So this is the emission if you use the solar cells and LED. I mean, all the emission comes from interface. Right? It's all CT emission. There's nothing of the pure 660 in there anymore, and the pure donor is a group. This is all CT emission. And it's the same. It's the same for all three. So the energy of the CT state has not changed, and you see the voltage has changed. So I was pretty excited about that, because it's the first ones we don't really fit into the line. Yeah, this is what it's saying. The energy of the CT state doesn't change, but the voltage almost changed by 100 millivolts by just using less donor. This is, of course, I mean, you cannot keep on doing this because you will at some point not have any donor left. We start calling these homeopathic solar cells. But until 5%, you can keep doing this and you don't really lose current. But if you take into account this F factor, so if you take that into account, you see again, then it becomes a line. So here we have to choose VOC by not changing any homolumen levels, by not changing energies of CT state, by just using less interface in this case. So we choose the F factor. Right, so if you look at this plot now, where are those points? Well, it's those three red points. So this one is a 1% one. So the energy of the CT state doesn't change. And we managed to lower this one. Instead of 0.25, it's now 0.15 for this one. We're not playing with this one. We don't know how to play with this one. So unfortunately, I was going to talk about this dark recombination, but I only have one slide because we don't know anything about it. Okay, I mean, maybe as a optical spectroscopist, we look at light coming out, and this is dark recombination. It's difficult to say something about the dark recombination if you look at light. So, but it's a fact what we see for all these polymer fluorine solar cells, and also for the co-evaporated one, the good solar cells. Every time the quantum efficiency of electroluminescence, and it's all CT emission, is really weak. That's why not so many people actually study this, because you need to be able to detect it. It's really weak. The quantum efficiency is 1/1,000,000 or lower. So that means that your VOC loss due to all these additional non-radiative recombination pathways is bigger than 350 millivolts at room temperature. I mean, you can lower this by just cooling it down, but that's not room temperature conditions anymore. You don't want to cool yourself. So, unfortunately, this is the only thing I can say about the dark recombination. Possible sources of dark recombination. Maybe the electrodes. If your electrodes are not the right electrodes, they might induce non-radiative recombination. Sometimes certain voltages depend on the electrodes. That's where this one. That's where electrodes. Maybe there are traps in the material which we haven't taken into account. They can be intrinsic or extrinsic. They can maybe be purified out. We try purifying, but usually you don't see any changes in this. Or, and this would be the worst thing, maybe it's intrinsic. Maybe to get a lot of current coming out of your solar cells, so to have a good short circuit current, maybe it's unavoidable to have so much dark recombination. So this would be the worst. And this is what I say here. So maybe to get the good current, somehow we have to sacrifice EQEL. At least empirically, that's what you observe. But we don't really know a mechanism behind it. So we're not playing much with these dark recombinations. We only know that it's a lot. They count for 35 volts loss. So if you want to study something, study that. So this already reaches my conclusion. So remember that, yeah, for the current donor-acceptor solar cell, there's a huge loss between the energy of the CT state and the open circuit voltage. It's 0.6 volts. And we know more or less where it comes from. We have some techniques to identify it. We don't know much about non-radiative recombination. We know if you push it down, the intensity, you can increase your voltage a bit. But I don't know if going to less interface is the way to go. Well, if you have high acetone diffusion lengths, it's maybe a good idea. Well, on top of that, you lose this one between ECT and VUC. On top of that, there's also a huge difference between the energy of the CT state and the gap of the main absorber. So you don't even absorb much light until here. So that energy here, between the gap of the main absorber and the energy of the CT state, that one you lose too. So another energy loss. So what we want is to shift this one as close to the absorber as possible. And that's what I will talk about in my third talk. If we do that, if we then can keep the current or not. And the last point, that's what I talked about. If you have more order in your system, it seems, you decrease the energy of the CT state. And you decrease the that was the last slide. Thanks.
Questions? Cephas.
Oh, yeah, just a comment. Koen, very nice talk. The device where you had C60 doped into TAPC W60, I actually met the guy who did that one. He came from a group where he didn't have access to all these exotic materials. He's trying to think of what he could do. So his goal was to make a device that was something between a Schottky junction and Volcano junction. So the reason why that device with low interface works is because the monoxide C60 interface is Schottky. So he can drive out the carriers and get away with using a reduced interface. Do you think that this kind of approach will work for, say, a polymer Volcano junction solar cell, going heavy on C60, going light on the polymer donor phase, and trying to use some Schottky junction to scoop the carriers out?
Well, maybe first of all, just the regular polymer fluorine solar cells, they have a lot of fluorine, right? As some of the materials, they have 80% PCBM or even more. So usually it's helpful to have more fluorine than polymer. Of course, when I saw that, I immediately tried it.
Yeah. Yeah.
But it doesn't work really well. So do I think it works? I mean, maybe theoretically, but practically, I wasn't able yet. Even more PCBM in the solar cell. I don't know if it's a really good idea economically.
Well, could it work the other way? Could you do heavy on the donor, light on the fluorine, and make a Schottky junction between the polymer and...
Usually they add so much PCBM. If you see the optimization, the polymer fluorine stoichiometry, it's always heavy on the fluorine. So empirically, for some reason, I don't really have a reason behind it. For some reason, low fluorine content doesn't really work. But, yeah, we should surely investigate why this is.
Natalie?
You showed Mike that the CT length, which you shifted, I think, when you changed energy levels.
Yes.
However, both of those compounds, I think they're more amorphous. How much is the microstructure influencing the effects you see?
You mean, yes. Usually, when, for example, this microstructure, the annealing of future HT or the added fluorine, that's in the range of 0.1. You're right, the difference between this PCBM and PCBM is also in the range of 0.1. It was low with future HT. There, I think, it's really anything.
Then possibly my question was also when you talk about interfaces, which ones do you talk about? It's more like the molecular ones? Or
That's a good question. I feel that this interface, the CT state, is delocalized over more than one molecule, at least on the donor side, and even more than one molecule on the acceptor side too, because it's effective. If polymer stacks, the energy lowers. To me, this means it feels the whole field the rest of the crystal. So to me, I haven't really specified it, but it's a good question. I think it gets more delocalized, and the interface I talk about is about not the one I drew actually in the beginning, not one fluorine, one polymer, but really phases.
So Koen, just to follow up on that point, have you ever looked at these molecular donor-acceptor materials where they're covalently linked and the distance is known?
No. Would be great. And the nice thing with those is you can study them in solution. So you can study them, you can basically isolate them, so you can turn off like dissociation pathways or CT states. You can get rates of electron transfer. That would be useful.
More? Okay, let's thank Koen one more time. We start again at 2. We have 18 minutes.